Let's take a look at our first application for Schrodinger equation, finding wave functions and energies for a particle in a box. So recall Schrodinger's equation, Hamiltonian operator operating on psi equals energy times psi. We can write out our Hamiltonian operator, minus h bar squared over 2m times second derivative with respect to x of psi plus v of x times psi equals e of x. And simplest case, let's just set our potential energy surface equal to 0. So we've just got a wave function that can sit on a perfectly flat potential energy surface, nothing making this more complicated. So we can rewrite this, minus h bar squared over 2m times the second derivative with respect to x squared of our wave function plus 0 equals d psi. We're going to solve this just like we've solved other equations back in chapter 2. And we're going to do that by letting psi equals e to the alpha x. This is an x. So if we let psi equal e to the alpha x, substitute that in, we find minus h bar squared over 2m times second derivative of this with respect to x is alpha squared e to the alpha x. That's just 0 equals e times e to the alpha x. We can cross those out. And we find alpha equals plus or minus I root 2me over h bar squared. So we have a solution for alpha. And we're going to maybe simplify this, and we're just going to say let k equals root 2me over h bar squared. Maybe we can write that one more way. We can write this as 2 pi root 2me over h. And you'll see later why we chose to pull out this 2 pi and h as opposed to using h bar. So we have our solution for the wave equation. Psi of x equals c1 e to the ikx plus c2 e to the ikx, or expressed as sines and cosines, c3 cosine kx plus c4 sine kx. This is our general solution for v of x equals 0. Now, this is a really general solution, and every time in classical wave equations, we always introduce some sort of boundary condition. And here we're going to introduce a boundary condition. So it's very similar to what we used for a wave on a guitar string. We're just going to put in the requirement psi of x can only exist between x equals 0 and x equals a. So here we've got an area where a wave function can exist, 0 and a, and we've got some sort of infinite wall out here. So this is analogous to a hard wall at edges of our classical string. And this is equivalent to an infinitely high energy barrier at each edge. Now, if that's the case, this imposes the mathematical boundary conditions that the wave function has to go to 0 at the edge. So we have psi of x equals 0 is 0, and psi of x equals a is also 0. Well, this first boundary condition we can satisfy by using our sine terms from our wave function we solved for before. And this one, well, we've got to make sure that in order for these wave functions to fit into the box, they need to be integer numbers of half wavelengths. So our boundary conditions, knowing that psi is some set of sines and cosines, tell us that a wave function has to be sine n pi x over a. That's its functional form to fit in this box. And we got that from the boundary conditions. Now, we also know that we can relate this to our energies from our wave equation. So we also know that psi equals sine of 2 pi root 2me over h x. And this is from our wave equation with 0 potential energy. So if we want to solve for energy, well, we can just set these equivalent to one another, and we'll see n pi x over a equals 2 pi root 2me over h. Well, if that's the case, we can solve for our energies, and our energies are then given by, with a little bit of rearranging here, h squared n squared over 8m a squared. So these are our wave functions. They're half wavelengths, they fit into the box. And these are energies. These are our eigenvectors and our eigenvalues. And so for this particle infinitely confined to stay in this box, we actually then see that our energies are quantized. Every wave function with a different n has its own energy. So there's our first wave function. I'll just make this dotted. Our second wave function, this is energy of n equals 1, energy of n equals 2. Here's our wave function. I'm just going to plot it right on top. And up here, these are getting higher and higher much faster because they scale as n squared. This is our energy of n equals 3. So here's our energy scale on the y-axis, and our psi of n equals 3. So for a particle confined to exist within a box, it naturally falls out from Schrodinger's equation that our energy levels are quantized and only certain energy levels are allowed.